In math, we spend a lot of time rewriting numbers, but now we're looking at how two quantities change together, like time and distance on a bike ride. This table tracks Jordan's recent ride. We have time in minutes, which is our x value, and distance in miles, our y value. To understand the relationship between these numbers, we divide the y value by the x value. You have to check every single row to be sure. 2.5 divided by 10 is 0.25. 5 divided by 20 is 0.25. 7.5 divided by 30 and 10 divided by 40 both give us that exact same 0.25. Because the distance is always the time scaled by the exact same fixed number, this relationship is proportional. We call that constant multiplier the unit rate. It tells us Jordan is riding 0.25 miles every single minute. We can take that exact same idea and plot it on a graph. But does any straight line represent a proportional relationship? This image shows two straight lines. The one on the right represents a taxi fare with a $3 starting fee. The line is perfectly straight, but it is not proportional. The single most useful test you have is checking the starting point. At zero distance traveled, you still owe the $3 fee. A truly proportional relationship requires that zero distance equals zero cost, meaning the line must pass directly through the origin at 0, 0. If a line starts at a baseline fee, or any number other than 0, it might be linear, but it fails the test of proportionality. Looking at a graph of Jordan's ride, the line passes cleanly through the origin. At 0 minutes, he's ridden 0 miles. We can extract his speed from this line by picking a clear coordinate pair, like 40, 10. The unit rate is always the vertical change divided by the horizontal change, the rise over the run. Keep the y value on top of the division, because we want to know how much distance he covers per single unit of time. When we take a rise of 10 and divide it by a run of 40, we get 0.25. The physical slope of this line and the unit rate from our earlier table are the exact same concept. Once we have that confirmed unit rate, writing the algebraic equation is straightforward. Y equals 0.25x. Now that equation gives us predictive power. If we want to know how far Jordan travels in 100 minutes, we multiply 100 by 0.25 to get 25 miles, without needing to plot a single new data point. This chart shows a new relationship, skipping the data table entirely. Pause here and try to find the unit rate directly from the line. To solve this, starting from the origin, we track a horizontal run to 4 and a vertical rise to 12. Dividing that rise of 12 by the run of 4 gives a unit rate of 3, meaning our equation is y equals 3x. You can now fluidly read relationships straight off a blank graph. Let's test these skills across formats. Here are 4 practice questions covering tables, graphs, extracting rates, and equations. Pause and solve them. For question 1, the table is proportional with a unit rate of 3 because all ratios match. For question 2, the answer is no. A straight line passing through 0, 4 is linear, but since it misses the origin, it is not proportional. In question 3, dividing 15 by 6 gives a unit rate of 2.5, creating the equation y equals 2.5x. For question 4, plugging 12 into y equals 8x yields 9 to 6. A relationship is proportional if its graph is a straight line through the origin, and the unit rate is just its slope.